In this video, we will give an intuitive introduction to a particle-based non-Newtonian solver and then present additional visual results of our experiment. Our solver focuses on the non-Newtonian behavior simulation, which is a classic topic in graphical community. Compared to other works, our work stands out in the following three aspects. First, our method is purely particle-based. By simply modifying the stress term of NS equation under SPH framework, our solver covers a wide range of rheological materials, including substance from fluid-like to solid-like. Second, we have implemented 6 classic shear-dependent viscosity models. These models are able to simulate shear thinning, shear thickening, and Behem fluid behaviors, which collectively encompass the majority of non-Newtonian phenomena. Third, we elegantly and concisely integrate viscosity, elasticity, and plasticity into a unified framework. We utilize the generalized Maxwell model to vividly and physically meaningfully interpret our constitutive model. Unlike Newtonian fluid, non-Newtonian fluid has nonlinear stress-strain rate relation. There are 2 types of nonlinearity: time-independent and time-dependent. For time-independent nonlinearity, we can use the shear rate-driven models to give a spatially variable viscosity to model it. As shown in the diagram, shear thickening fluids exhibit an increase in viscosity with increasing shear rate, and vice versa for shear thinning fluids. Behem-type fluids, including Casson fluids, have a non-zero stress at 0 shear rate. For the time-dependent nonlinearity, we modeled viscoelasticity and plasticity with generalized Maxwell model, which will be discussed later. The major difference between our algorithm and others lies in the inclusion of both viscous stress and elastoplastic stress in the Navier-Stokes equation in our solver. This is the key feature that enables our solver to handle non-Newtonian behavior. We introduce generalized Maxwell model to provide a physically meaningful explanation of the viscosity, elasticity, plasticity, and their interrelation. In this diagram, the spring represents elasticity, the slider represents plasticity, and the dash pod in the bottom branch represents viscosity. Total stress is divided into elastoplastic stress and viscous stress. The elastoplastic stress is controlled by the elastoplastic strain, which is further divided into elastic strain and plastic strain, while the viscous stress is controlled by the viscous strain rate and viscosity. From now on, we will demonstrate several experiments and comparisons. We draw a comparison with 2 state-of-the-art frameworks, FLIP by Shao et al. In 2022 and MPM by Fan et al. In 2019. In this scene, where high viscosity honey drips from strawberries, we observe that our solver performs as well as FLIP and even produces better results than MPM when handling high viscosity substance. Our framework demonstrates comparable results to the other 2 frameworks in simulating the falling of a viscous cow. Our framework not only handles high viscosity fluids effectively, but also supports shear-dependent viscosity, viscoelasticity, and viscoplasticity. This extends its capabilities beyond traditional approaches for modeling complex fluid behaviors. In this scenario, 8 viscous armadillos slide down a slope. Each armadillo adopts a different shear-dependent non-Newtonian model, including the Casson model, power law model, Corral model, Cross model, Behan model, and Herschel-Buckley model, among others. We have successfully replicated a classic non-Newtonian phenomenon, the impact of a golf ball dropping into a mixture of cornstarch. Due to its shear thickening properties, the ball experiences a rapid impact followed by a slow sinking motion. Our simulation closely matches the recorded video results, demonstrating a high level of consistency between our model and the real-world observations. We have successfully replicated a classic non-Newtonian phenomenon, the impact of a golf ball dropping into a mixture of cornstarch. Due to its shear thickening properties, the ball experiences a rapid impact followed by a slow sinking motion. Our simulation closely matches the recorded video results, demonstrating a high level of consistency between our model and real-world observation. If we keep other setup and change the fluid from the cornstarch water mixture to ketchup, which is a shear thinning fluid, we will see completely different behavior. With implementation of diffusion equation, our solver is able to simulate phase change such as ice cream melting. Thanks to the particle representation, our solver can easily handle the topological change. For example, the chocolate bunny is cut while melting. Thank you.